Thank you very much for the invitation, and it's really been a very, very pleasant, delightful day at this very impressive campus you guys have here. I've said many times I haven't seen a, quote, undergraduate school with the facilities like you have here at Richmond. And I've been several places, certainly Hendrix College doesn't have this. Anyway. Okay, so what I'm going to tell you about is a technique called a phenomenon called dynamic nuclear polarization. And the subtitle of this talk is Why Two Electrons Are Better Than One. And as we go through the talk, this will become clear what I'm talking about here. And it's actually a biradical polarizing agent that gives us a much higher sensitivity than you would get normally out of this technique. So an outline of what I'll tell you is shown here. I'd like to go over some background and rationale, show you the kinds of instrumentation we developed for dynamic nuclear polarization. We built essentially all of this with our own group at MIT. It's now becoming commercially available, though. I'd then like to actually tell you, we're going to skip this topic for a moment, and tell you about polarizing agents and mechanisms. And that will introduce the idea of a biradical polarizing agent, which, as I said, gives you an enhancement of like 170, and we've actually seen up to maybe 340 in Nmr spectra, and discuss two mechanisms, the solid effect and the cross effect. Then I will return some applications, and then if time permits, we'll talk about polarization of low gamma nuclei, and in particular, direct polarization of carbon and deuterium. So that's what this is the material we're going to go over. And the people who really did this work are shown here. I'd like to acknowledge Xander Barnes, Con Hugh, Melody Mack, Yo Matsuki, and Vic Bajaj. They're the people who did most of the work I'll tell you about. There's a group that we collaborated with for a long time, Richard Timken, who's helped us build Gyrotrons. I should also mention Melanie Rose and Werner Moss, who are down at Bruker. And then Tim Schwager and his colleagues have made biradicals for us. Paul Tordeau, who's a chemist in Marseille, has also done this. And these are the groups of people who have worked on some applications, which I'll tell you about bacteriorhodopsin. And this is an amyloid protein, phosphatidylinositol 3 kinase, and that's worked with Chris Dobson. Okay, so let's go over some background and rationale here. Now, if you're an Nmr spectroscopist and you want to have better signal to noise in your spectrum, and that's always a problem with Nmr, signal to noise, what you have done for probably most of the past 50 years is just to go to higher and higher magnetic fields. So the polarization in an Nmr experiment, which is the number of nuclei up minus those down over the sum, all right? And in the high temperature limit, you get this hyperbolic tangent form right there. The polarization is given by gamma h bar b naught, okay? So if you want a larger polarization and therefore a larger signal, you have sort of two choices. You raise the magnetic field, or you can lower the temperature, all right? Now, so what people have done is mostly raise the magnetic field, and you can go from 500 to, say, 700 up to maybe 900 megahertz. And that's the strategy people have used. And going from 5 to 9 gives you approximately a factor of 2 in polarization, all right? But the problem with that is you can get this magnet, say, at 500 megahertz for maybe 200,000 or so now. But the higher magnetic fields, like 900, cost you a lot more money, maybe $5 million. The next generation, which is probably going to be about 1.2 gigahertz, is going to go up to maybe 15 to 20 million. So it's getting very costly to simply pursue this strategy further. So what we've done is employ an old idea, all right? And that is the fact that electrons have a much higher polarization than nuclear spin. So electrons have a magnetic moment that's 660 times that. Proton is about 2,600 times larger than the carbon-13 nucleus. So the formulas for the polarization are the same, just exactly what I showed you here before. But in fact, in this linear regime here, you can get a factor of up to 660 or so larger polarization. And the polarization curve is shown right here. It's linear. And then if you get down to a low enough temperature, maybe 2 or 1 degree Kelvin here, at a high magnetic field, the electrons are completely polarized. All right? So what we would like to do then is make a sample with electrons in it, dope it with electrons some way, and then transfer this polarization from the electron spin reservoir down to the nuclear spins. Now what you have to do in order to accomplish this is you have to irradiate the system with high-frequency microwaves, and that'll become clear later. So for a G equal to electron, that turns out to be about 28 gigahertz per Tesla. So a 10 Tesla magnet, which is like a 400 megahertz magnet, that means you need 280 gigahertz microwaves or so. Those microwaves are about a millimeter or so in wavelength. So this is a unique regime in the electromagnetic spectrum. It's one that's actually been fairly blank. Okay, there are very few sources that operate in this regime, and that's actually been an impediment, a major impediment to accomplishing this polarization transfer that I listed here. Now what I'd like to do in the next 2 or 3 or 4 slides is show you that this actually works, all right? Give you some results up front. This really does work, this idea. And then I'd like to explore the mechanism of the equipment and then the mechanism of how you make this work and work better, this effect, okay? So if you want to make a sample for this, and we work almost exclusively on biological systems, membrane proteins, we work on amyloid proteins and many other systems like that. So you can take a membrane protein, for example, bacteriorhodopsin, and you cryoprotect it with glycerol. As I've shown here, we put in 60-40 glycerol because that always forms a glass. You dope the system with paramagnet. This just shows a monomeric nitroxide free radical 4-amino tempo, and then you freeze the sample. So you have these electrons going in a cryoprotected sample. Now you can use this approach for essentially any system, water-soluble protein, an amyloid fiber, or whatever you want, a surface that actually works with that. And so what you're going to do is you're actually going to polarize the solvent, the water, and the glycerol right here. And as I'll show you later, this polarization will diffuse throughout the entire sample and light up the entire macromolecule. We'll talk about that a little bit later. So this is how you make a sample. Now, I want to give you an example of how this might work. And this is the simplest case. This is not the case that's the best way to go by any means, but this is a simple situation, and it's called still called solid state effect. Now, what we're assuming here is that we have a single electron and a single nuclear spin. All right. So you have a 4-level system, as I've shown over here. All right, with these energy level transitions. So these guys right here would be Epr transitions, the black things. So you're flipping, so the first, the plus here in this ket, and the minus in these kets is the electron transition going from minus to plus, and then the nuclear transition in the second sign in the ket is a plus to a minus, okay? So electrons go from minus to plus, and nuclei go from plus to minus in this flow, all right? Now these are closely spaced energy levels. So it's possible you can have state mixing, all right? So if you do first-order perturbation theory treatments, you look at the electron-nuclear dipole Hamiltonian, you have a term in it that looks like this, SZ, I plus minus, and that mixes these two states. And so what you get then, normally these red transitions are not allowed, but with the mixing coefficients in here, these actually become allowed. And the matrix element gives you a coupling between them, and it goes with 1 over omega naught. Now, if you remember some elementary quantum mechanics, this actually goes, the transition probability goes as the square of this mixing coefficient, so you get an enhancement that goes as 1 over omega naught squared. So this mechanism, while it's very interesting and illustrative of the technique, it's not a really great thing to use at high magnetic fields. If you go from 200 to 800, you go up a factor of 4 in magnetic field, you go down a factor of 16. So this is a good way to understand it, but it's not exactly what you want to do. Now what happens up here? So these are the Boltzmann populations of the different states represented by the size of the green ball. And so we're going to irradiate this transition right there, the so-called double quantum transition, this right here. And so you saturate these two energy levels, right? So you equalize the populations. And what you see is, lo and behold, when you do that, the population difference across these NMR transitions here is increased. So that's actually going to give you a positive enhancement, right? Now you can go to the other side of resonance, and you can hit this transition, the so-called zero quantum flip-flop transition, that's right here. And again, you equalize these two populations, and you see you get a negative population difference, so you get a negative enhancement. So on one side, you get a positive enhancement of the polarization, and the other side, you get a negative enhancement. All right. So that's sort of the way. Let me just actually draw this for you. So what we're saying here is that we're plotting enhancement now as a function of magnetic field, and it actually will look something like that. And that's a so-called solid effect. All right. Now, this is one way to do this sort of work. And this just actually shows you some experimental results. So we turn on the microwaves here, in this case 140 gigahertz. We saturate the proton polarization with a long train of pulses. And then there's a delay. And during that delay, polarization actually builds up in the proton reservoir. All right? We then transfer from the proton spin system down to the carbon, as I've shown right here, and you just look at the free induction decay. And these are just a series of 1D spectra. This is just C13 urea. It's not a very interesting compound. But it has actually a biradical in it, not a monoradical, and this is a different effect. But it just shows you that over a period of about 15 seconds of radiation here, you can build up the polarization, and you can get an enhancement of 175 in this case. All right? So this shows you that, in fact, this effect really does work. All right? Now, somebody's mother is calling, right? Okay, so you get a factor of 175, right? Now, I promised you a factor of 660, so this is really only 27% efficient. So we really have a long way to go in the development of the technique, the polarizing agents, the instrumentation, and so forth, to get up to the maximum value. Now, this is urea, which is a nice test sample. If you do NMR, you always have to have a test sample to make sure your spectrometer is working. But this technique actually does work on real systems. All right. So these are some enhancement spectra of membrane proteins, right? Bacteria rhodopsin, as I've shown right here. So this is the normal one-dimensional magic angle spectrum of C13 labeled bacteria rhodopsin. It's blown up by a factor of 10. That's the microwaves off. And you turn the microwaves on, and you get an enhancement here of about plus 50 or so. So this just compares. You can see this guy's blown up by 10. It's about a factor of 5 higher here. So you see you're getting an enhancement of approximately 50 or so. And if you go to the other side of resonance, like over here, you actually get a negative enhancement. It's slightly smaller, but this is a real system, a membrane protein, an intact membrane protein, and we can polarize that. Now, we've also done this on soluble proteins, like I showed you before. Now, this is a very busy slide, but this illustrates an important point in which we've actually deuterated the protein. That's actually very easy to do these days. You biosynthetically C13N15 label, and if you grow bugs in deuterated water, D2O, you can actually deuterate the protein. This is an alpha spectrum SH3 domain. And what I want to show you, what you notice, is that at 211 megahertz, you see you get an enhancement right there of 200. This is a number in enhancement of about 350. And if we go to higher field, as I said, the enhancement's going to go down, but you see 120 and 148. So the numbers you really want to look at are right here. So these are quite substantial enhancements in one-dimensional spectra of proteins from something like 120 to 100, 200 or so, right? So this effect really works. We can polarize model compounds. We can also polarize membrane proteins and other proteins as well, all right? Now, people say, so what? You know, it's nice. You have to do some science with this, all right? But let me just remind you what increases in sensitivity like this have done for magnetic resonance or for science in general. So first of all, there was Ernst and Anderson who introduced Fourier transform NMR. That gave you an enhancement of something like 10 to 100. And of course, in 1991, that won Richard Ernst a Nobel Prize. There was an indirect detection technique by Bodenhausen and Rubin. That was a factor of 30. This allows you to do protein structures in solution NMR because of indirect detection. There's a polarization transfer experiment across polarization and a net that won a couple of Wolf Prizes, and so forth and so on. And Kurt Wittrick, with his Trozy experiment, he got much better resolution, factor of 5 or so. But these advances have had, I mean, I showed this to my dean and department head, they don't know much about NMR, and I tell them, you know, this is something important. You get a lot of signal noise, you're going to be able to make a big impact on science. So we have enhancements, I'll show you, of 50 to 400 or so, and what this does, it saves you factors of like 2,500 to maybe 160,000 in time, okay? And that makes all the difference in the world in the kind of science that you can do, the kind of problems that you can study, okay? So this is sort of background to Dmp and shows you that it actually works, all right? Now let me tell you just a little bit about the instrumentation, because someday I'm sure you guys will run into this, so you won't be too surprised about what we do, all right? So they're basically, in addition to sort of a normal NMR spectrometer, there's sort of 4 additional pieces that you need to put together. One is this Gyrotron microwave source that I mentioned, alluded to earlier. Another just is a corrugated transmission line, and then a low temperature probe, and then of course you need a polarizing agent, a suitable polarizing agent, and this is a biradical, what we call BTBK, all right? So now, if you go to your local microwave store and ask for a microwave source that runs between like 150 gigahertz and something maybe like 600 gigahertz or so, these are the choices that you have. They're gun diodes and impact diodes. Actually, the preferred choice for those these days is the Virginia diodes over in Charlottesville, all right? You can get lasers, but these things don't really have a lot of power. So what you need, for reasons I'll tell you in a moment, is something like 10 to 100 watts. And so gyrotrons, which is a cyclotron resonance maser, I'll show you in just a second, are really, at least at this point in time, the device of choice. And we've built 3 of these at 140, 250, and 460 gigahertz, and we have something about running at 330, and we're also building something at 527 gigahertz, and this corresponds actually to 800 megahertz NMR. So this technique, a lot of what I'll show you today was done at 200 and like 380 megahertz proton frequencies, but it is scalable, okay? It's going to scale up to the highest magnetic fields that we have available. So this now is what a gyrotron actually looks like. It's actually a vacuum tube, a big vacuum tube, long vacuum tube, and it's immersed in a superconducting magnet. And so you generate electrons down here on an electron gun, and you put a voltage across this, maybe 10, 12, 13 kilovolts. So this is ground, and you put this at minus 12 or 13 kilovolts, and electrons get accelerated through the magnetic field. And when they go through the magnetic field, they start to gyrate. That's why it's called a gyrotron. They spin, they bunch up, and microwaves come out the crossbore port here, and the spin electrons get collected up here in the electron beam collector. So this is the actual tube. You can see the window right there. And this is the superconducting magnet with the gyrotron immersed in it. And you see there's a crossbore, a hole in the side of the dewar, and you put a waveguide into that, and the microwaves come out. Now, it took us a long time to build this, all right, a long time to make it work. And you can wonder, you can ask yourself, well, is there not a better, easier way? Well, this just shows you some data. This was taken with a gun diode, all right? And you can do experiments with a gun diode. So you can go to Virginia Diodes and buy a 20 or 30 milliwatt diode, and you can get enhancements of something like 10 to 30. But if you crank up the power higher up here, you can get up to, this is an enhancement of 185. So you can go an order of magnitude, a factor 20 or so, higher power if you have a gyrotron. And so the high power millimeter wave sources is really clearly preferable for DMP, at least at this point in time, right? So that's why we've gone to the trouble to develop this microwave source. And very importantly, it's scalable, as I'll show you, up to very high frequencies, right? Now, you also need a kind of a funky looking Nmr probe, and that's what this is right here, which was built by Alexander Barnes. So this is a magic angle rotor, stator right there. This is a waveguide. You see this is a triple resonance probe. It does proton, carbon, nitrogen, and electrons. And this is a transmission line which is tuned to proton, carbon, and nitrogen. And then on the inside of it, we corrugate it and send microwaves up the center. So you see the microwave, there's a miter band that comes up like this. The microwaves come up and reflect off and irradiate the sample. Now, this thing on the front is just a sample eject mechanism. And the reason it's kind of unique is because you have to eject the sample from 90 Kelvin, all right? Everybody knows you drop the sample in an NMR magnet and you blow it out with air. Well, here we have to do it at 90 Kelvin, which created a lot of interesting problems, I would say. So we also irradiate the sample for photochemical experiments with a laser right here. This is a 532 green laser going into it, all right? So that's the kind of probe that you have to deal with. And you put it all into a vacuum jacketed dewar, all right? This just shows you the sample eject inside a cross section of it. The sample comes up here and out the top. You can see the coil here, the Nmr coil with the sample spinning at the magic angle. And you see the corrugated waveguide coming up here, and the microwaves come up, reflect off this mirror, and irradiate the sample. So that's really, once you get it done, that's all you have to do. So this is actually fairly straightforward, okay? Once you work out the bugs, all right? So this microwave circuit here has a Q of 1, all right? So that's why you have to have a lot of power, okay? So it has a Q of 1. So you need 10 or 20 watts in order to get a reasonable gamma B1 at the magnetic field, at the coil. And this is what the whole system actually looks like. A lot of wires and cables and so forth hanging off various and sundry things. But we have a 250 gigahertz gyrotron, a transmission line running across the room. It's right here. And the probe, it's actually out right now, but it has this, I've shown you probes of that, pictures of that, and you radiate the sample at the top. Now, this is 250 gigahertz, 380 megahertz, and I didn't point it out, but this particular gyrotron was configured to work at 460 gigahertz, which corresponds to a 700 megahertz NMR system. And in fact, we've actually just this past summer gotten this working, so you can see a picture of it here. The 700 magnet is really quite large. It has a very large fringe field, but you can see the gyrotron and the corrugated waveguide. And this actually all works. So these were some of our very first results here, which show you an enhancement of -40. So this is a microwave off spectrum blown up by 40. That's a microwave on. And we're on the negative side of the enhancement profile. But you see as the power is going up linearly, so the more power, if we can get more power into the system, and we know we can do that, this number is likely going to grow. So this is our first step in towards 7, 8, 900 megahertz. As I say, we're on the way now to 1 gigahertz and higher. Okay, so that's the instrumentation that you need to do this sort of stuff. Now let's talk about polarizing agents and DMP mechanisms and how you actually make the experiment work. Right? So once you have a system with electrons in it, a biradical or monoradical or even a metal ion, there are lots of ways you can do to transfer polarization. So you can start from the electrons, as I've shown right here, and you can go over to protons, all right? And then you can cross-polarize and transfer down to C13. And this has a sort of lifetime or rate constant associated with it, whatever the rate constant of about 5 seconds. You can transfer directly to carbon, all right, and ignore the protons. You actually get larger enhancements here, as I'll show you, but it takes you longer to do that, all right? And then another possibility these days, which is actually quite exciting, is to take electrons and to go to deuterium. There are lots and lots of deuterated proteins available. You can polarize deuterium and then transfer to C13. So these are some of the possibilities that you can exploit when you're doing DNP. And so we're going to go over each of these in detail and show you actually how they work, right? So this is the mechanism that I showed you a few minutes ago, the so-called solid effect. It was originally introduced in 1959, 1960 by Aberdeen and Proctor and Jeffries. And as I said, it's one electron, one nuclear spin polarization mechanism, and it goes at 1 over omega naught. Now, in order for this to work well, okay, you actually have to have a very narrow line EPR spectrum, okay? So I've shown you tempo as a possibility, which is right here, but for a solid effect experiment, you have to have a narrow EPR line, and this you get this only in a couple of compounds. This is called bis-diphenylallyl right there, and we have some new versions of this which are actually water soluble, but this is a kind of spectrum that you have to deal with, all right? Now, more generally, more stable radicals in solution are guys like this, so the tempo radical, all right? This has been used in EPR spin labeling for years, introduced by Hardin McConnell and so forth, and so these are very robust systems. And you'll notice, though, that they have a much broader EPR spectrum. So whereas this is maybe 21 megahertz or so wide, this guy here is about 600 megahertz wide, all right? Now that has consequences. It completely changes the mechanism of the polarization transfer. So this just shows you a little bit about what I mean, all right? So this is the schematic of the EPR spectrum right here, all right? And it's a 600 megahertz wide spectrum. And so what we do is we would, so this is a busy slide, so this is part 1. In part 2 over here, we would actually say irradiate over here at, say, electron 1, all right? Now, because of the breadth of this guy, it's 600 megahertz, and our proton Larmor frequency is 200 megahertz, okay? So it's a factor of 3 wider than the proton Larmor frequency. We can fit the proton frequency in here. So there's another electron in this spectrum, which is separated by the nuclear Larmor frequency, right? And this is a so-called matching condition. So when you have a wide spectrum, all right, you can actually employ another mechanism that's called the cross effect, which we're going to explore in more detail here. And it involves irradiating one electron, which is dipole coupled to another one. So you flip one, and then you flip the other electron, and the energy difference between these two goes into the nuclear spin system, and that does the polarization for you. All right, and so this has the advantage, too, that it goes as 1 over B naught, or say 1 over omega naught. So it doesn't have the strong field dependence that the solid effect displays, all right? So now, we started thinking about this when we were working with tempo and monomeric polarizing agents like 4-amino tempo. And what you realize is you have sort of 2 classes of two classes of tempo molecules here, okay? So we knew we had this one electron flip, the other electron flip. The difference goes into the nuclear spin system. But you look at this, you have 2 classes, okay? So you have these weakly coupled guys. So these are the electrons right here. So there's a class that are weakly coupled. They're far apart. So one guy's sitting on one side of the room here, the other on the other. And they really don't do anything for you. So these weakly coupled electrons here, they don't help you much with the DMP, all right? The ones that do help you a lot are these others, the more reddish polarizing agent here, and these are strongly coupled. So they're close together. They can communicate with one another. They have an electron-electron dipole coupling of maybe 20 megahertz or so. And they actually do the polarization for you. Now, these are going to turn out to be quite large molecules, and so they actually will not penetrate a membrane protein, okay? But this is the kind of situation that we actually are going to deal with, okay? So when we realized this, okay, and we also decided to put everything in this sort of 60-30-10 D8 glycerol D2O water mixture, all right? Then we hit on the idea that why not just hook two of these guys together, okay? So we make a biradical polarizing agent, and this was first done by Con Yu and Bruce Yu, all right? So Con was a student in my group. He had a friend from undergraduate school in Taiwan, Bruce, who was working with Tim Schwager, and over 3 weekends they got together and made 3 different molecules with N equal 2, 3, and 4 here. And these are called bis-tempo N-ethylene glycol biradicals, okay? And they were used extensively for EPR studies of dynamics in the 70s and been sort of sitting around ever since then. But in fact, it's this biradical, all right, that actually allows you to get this very large enhancement, this factor of 175 that I mentioned before. Now, the maximum, just to calibrate you, that we've ever seen with monomeric tempo was about 40. So this is about a factor of 4 larger, 4.5 larger than what you get with tempo. You can also decrease the concentration from like 40 millimolar down to about 10. So this removes electron nuclear dipole broadening, which is very important if you want high resolution. And again, this gives you a factor of this 27% efficiency. Now, the BT-NE series is not very water soluble, so Tim Schwager and his colleague Chun-Sik Song made this molecule, which is called Totapol. It's tempo-oxy-tempo-aminopropene 2-all, and it's very nicely soluble in water glycerol. And this is what we use in essentially all of our studies these days to polarize amyloid, to polarize membrane proteins, and so forth. All right. So this is a really nice molecule to have around, and it shows you the real benefits of collaborations with an organic chemist and a physical chemist. All right. So I've shown you then that these guys give very much larger enhancements, and let's explore now exactly how this actually works. All right. So this is the EPR powder pattern that I showed you before, and these are various mechanisms of polarization, and we're going to focus on this guy right here, the so-called cross effect. For delta, the size of this powder pattern is very much larger. It's larger than the nuclear alarm frequency, and that's larger than the isochromat width here, the homogeneous width, these little spikelets. All right. So, as I said, delta here, this number is about 600 megahertz. Okay, and just to put some numbers on this, so the spikelet width, the homogeneous width here, the isochromat width, is about 5 megahertz. Okay, and the nuclear alarm frequency here is about 210, 200 megahertz. So we clearly satisfy this inequality. All right. So just to bring this all together in one slide, then. So this is the inequality. These are the numbers. All right. So you can irradiate one electron here. It's coupled to another electron on the other side of the powder pattern. And when you match this matching condition, as I've shown right here, then you have this one electron down, flipping up, the guy up, flipping down, and the nuclear spin is polarized in the difference. All right? And this was an idea actually introduced a long time ago by Kesnik in the Soviet Union. This was a paper that nobody knew about because it was only in Russian. At least I didn't know about it until quite recently. But he was actually the guy who actually proposed this, although he never really did it with a biradical. So anyway, this is the mechanism that you want to satisfy here. All right, and the nuclear alarm frequency, of course, fits inside here. So that's what you need. All right. Now, how do you get this frequency separation between the ends of two biradicals? Well, you do it via the G anisotropy, all right? So that's shown here, all right? So you have different nitroxides here. So if you take a nitroxide and you orient with the NO bond along the magnetic field, which is up, that will give you a frequency, a low frequency right here. If you turn it and it's sideways like this, the magnetic field is again up, you'll get a G value somewhere in the center here, and if you flip it over and the magnetic field is perpendicular, you'll get a G value up on the right-hand side, okay? So I don't know how well you can see this, but this shows you a Bt2E molecule with one half like this and the other orthogonal to it, oriented 90 degrees away, all right? So there's some free rotation, relatively free rotation, about a lot of bonds here, but there's a fraction of the molecules in the sample that satisfy this constraint, that so if you irradiate over here, they're going to talk to some guys over in this part of the powder pattern, and that satisfies that matching condition. It's just simply an orientation effect between the two ends of the molecule, all right? So that's what we're going to do. Now let's just look a little bit at the quantum mechanics of this, and this is a little bit harder to follow, but I'll go through it kind of slowly, so maybe we can all do it together. Again, we have energy levels, and we have 2 electrons in a nuclear spin now, so we have not 4, but we have 8 energy levels to deal with. And the green balls, again, show you the populations of those energy levels at equilibrium, all right? And you'll notice when we satisfy this matching condition right here, these 2 energy levels at the center are degenerate, okay? That's just, you have to work through the quantum mechanics to see that, all right? So they're degenerate, okay? So now we can irradiate one line in the spectrum. So we're taking an ideal case here where we have 2 narrow lines that are separated by this nuclear Larmor frequency. So you can irradiate one line, all right? And then you look at the effect over here on the energy levels. These are the Nmr transitions that I've shown you before. And when we irradiate that guy right there, what we do is we excite these 4 EPR transitions, and these are allowed transitions now, so there's nothing unallowed for it like there was in the solid effect. So those are allowed transitions, but these guys are degenerate. They're the same energy level. So when you hit this transition right here, okay, you are also going to hit this transition, okay? It's the same energy level. So what you're going to do is saturate these 2, you're going to saturate these 2, and then these 4 together, okay? So the populations, so you saturate those 4, so you equalize these 4 populations, all right? You equalize these 2 and these 2, and lo and behold, what you see, if you go through all of this, is that the population difference across the Nmr transitions right here is actually increased, okay? And that's going to give you a positive enhancement. Now, you can go do the other way. You can do the irradiate the other transition right there, and of course you'll get a negative enhancement. It's the same sorts of arguments. I don't want to go through it. And if you don't match the matching condition, in other words, if these guys are twisted with respect to one another in the wrong way, then what happens is that you break the degeneracy in the center here, and the experiment doesn't work as well. Okay? So this is a very simple-minded explanation, but it shows you how this so-called cross effect works. It gives us about a factor of 4 or 5 larger enhancements, so it's really the way to go. And this is why these 2 electrons are better than 1 when you're doing DMP. Now, what you do in a DMP experiment is actually sweep the magnetic field, as I indicated here, and this just shows you what we call a field profile. This is a field profile for the solid effect. This is, well, there's one right there too. And this is a field profile for the so-called cross effect with this biradical Bt2E here that Conhue recorded, and it gives you this factor of 175. And you can see here the difference in going from a monoradical, this is the tridal radical, which I haven't talked about. It gives you a solid effect. It gives you about a factor of 15 enhancement, and if you go to the biradical, you get 175 or so. It's more than an order of magnitude increase in their sensitivity. So 15 is already a lot. More people would kill for that. 175, you'll kill a lot more. Okay, it's really very, very important. Okay, and so you need to sweep to the optimal field up here in order to get the largest enhancements. All right. Now, this molecule, as I said, there's some flexibility around the carbon-carbon, carbon-oxygen bonds, so you don't have, you're not really doing a very efficient job. So what Paul Tordeau did, our colleague in Marseille, he actually made this guy, which is called BTBK, so it's bis, tempo, bis, ketal, so these two ketal groups in the center. And the way I've drawn it here is that this end of the molecule is planar, whereas this end of the molecule is vertical. Okay, so these are oriented roughly. This is a ChemDraw drawing, so it's not exactly accurate, completely accurate, but they're roughly at 90 degrees with respect to one another, and you can see the enhancement build up over here. That's the number we get, 250. So if we use this rigid biradical with orthogonal, roughly orthogonal nitroxides, we can go from 175 or so up to about a factor of 250. Now, this guy is only soluble in DMSO water, which is not right up here. It's just not a very good solvent for proteins, but I'll tell you about that later. But this is now 38% efficient, but it saves you in time a factor of about 62,000. So this is a huge effect for NMR spectroscopy. Now, we have made a water-soluble version of this guy for reasons which I can tell you about. It has sulfurs in it rather than the oxygens. It's a little bit longer. The dipole coupling is lower, so we only get a factor of 230 rather than the factor of 250. All right. So that's the way the so-called cross effect works. So you transfer polarization from the electrons to the protons, all right, and then to C13, okay? Now, we can also transfer directly from electrons over to C13, right? And if you do that, what you find, you measure the enhancements. Well, this is something called tridal radical. That's a narrow line radical. So if you just irradiate CW, do decoupling, and wait some time here, you can watch the build-up curve, and you get a factor of 325. So that's even larger. That's direct polarization at C13. The problem here is the time axis, okay? So to get up to the maximum, it requires you about 600 seconds, or about 10 minutes, okay? And the reason for this is the spin diffusion, something called the spin diffusion in the C13 reservoir is just slower. It's because the gammas, or the magnetic moments of carbon, are lower, and they're more dilute. Nevertheless, you can get a factor of 325, but that's actually a factor of minus 325, all right? And the reason for that is right here. It's the same logic that we use with the so-called cross effect. So this is the criteria that we want to satisfy, delta greater than omega naught greater than delta. But now what we changed is the nuclear alarm frequency right here. It's not 200, it's 52 megahertz now. So the number, if you go through the spectrum, the Epr spectrum, the number of electrons per unit Gauss here, okay, is actually highest over here. So the number of electrons per spectral division is highest over in this part of the spectrum. So if you can fit the nuclear alarm frequency into this part, you're going to get the highest enhancement there, the largest enhancement. And in fact, that's the case, so we satisfy this condition. And the carbon-13 alarm frequency will fit over into the left-hand side of this field profile and give you the largest negative enhancement. And that's shown here in the blue curve, all right? And again, though, it builds up rather slowly. This is C13 glycerol. It's a more favorable case. It builds up in about 100 seconds, right? Now, finally, you can transfer from electrons to deuterium. Okay, and then to C13, this is kind of interesting and amusing too. These are some magic angle spectra of deuterium powder patterns, and the deuterium powder pattern is very wide. Okay, it's about 200 or 300 kilohertz wide, so you get lots and lots of sidebands. But what you see is with our biradical, all right, it actually doesn't work as well as this monoradical tridal. All right, but that's actually, in fact, a factor of 4 difference. And in fact, if you use tridal radical, you can actually get an enhancement. It's something greater than 700. Now, this is hard to measure, okay, because you can't get an off spectrum very accurately. You average and average and average, and you have to blow it up by a factor of 70. But that's what the spectrum looks like. This is the on spectrum. It's just a proline sample, but you get something of the order of 700 or larger. Okay. Now, the reason for this is, of course, is that the deuterium Larmor frequency is very narrow, is very low, and you can fit that into the narrow line tridal spectrum. All right? Okay, and then you can transfer polarization from deuterium down to C13. Okay, so this actually shows you these field profiles. That's the cross effect, and then the deuterium Larmor frequency actually fits very nicely into the tridal spectrum as I've shown here. Okay, so this is sort of how DNP works. Okay, in this so-called cross effect, and this shows you why a biradical is in general more useful than a monoradical. Is much better. And now let's look. We have a little bit of time left at an application or two, and show you that this really is applicable to real systems. All right. Now, we've been studying bacteriorhodopsin. It's a membrane protein in our lab for some time. It's a 26 kilodalton protein. It's a retinal chromophore in it, shown right here. And it's supposed to be a light-driven proton pump. And what we want to know is does the mechanism of the actual proton pump, right? Now, so the way this works, there's a shift base right here in the center of the molecule, the protein, and it transfers a proton from there to an aspartic acid, and then it goes out to the extracellular medium. So you hit this with light, and you get this proton transfer case. And then the whole system recocks from the cytoplasmic side, the shift base reprotonates. All right? So this is, we're actually interested in the details of the mechanism. How does this proton actually transfer from this retinal chromophore down to the aspartic acids? Now, there's another interesting aspect of this. For many, many years, people have said this is a proton pump. All right? And it's been well accepted as a proton pump. But it could be a reverse direction hydroxyl pump. So you could pump water sort of backwards. You pump a hydroxyl ion this way, and a proton will just fall off in the other direction. In fact, from our Dmp experiments, we have some evidence of that. Right? But what we would like to do then, though, is understand the mechanism of proton pumping. And in order to do that, we're interested in looking at the shift base, which is right smack dab in the center of the molecule, right? The protein, right? Now, what I've been telling you all along for the last 40 minutes or so is that, in fact, we've been polarizing the solvent out here, okay? So we take these biradicals, totopol, BTBK, tempo, whatever, and we actually put that into the solvent, so the water glycerol solvent, and we polarize that solvent, all right? And then you ask the question, how in the world are you going to polarize the inside of the protein, okay? And this is a question that's come up on 5 or 6 of my NIH grant reviews, okay? So people ask it quite a lot, all right? And it's a reasonable question to ask, okay? Well, what happens is there's a phenomenon called proton spin diffusion. So if we actually build up polarization out here in the cytoplasm or in the extracellular medium, it actually diffuses in to the center of the molecule. And it's just this mutual spin flips amongst the proton spin reservoir. It's homogeneously broadened, it's dipole coupled, and the proton polarization diffuses in. So schematically, what I'm talking about is here. So this is a schematic representation of bacteriorhodopsin. Here are the lipid molecules, and out here on the edges you see the polarizing agents and the glycerol, the cryoprotectant. This is approximately 50 angstroms or so, maybe not quite that size, but during the polarization process, what you do is you see the polarization diffuse in to the center. It lights up the whole molecule. Okay, so that is actually the spin diffusion process that actually occurs. Right? Now that's an animation. Is that really happening? Well, you can look now very simply at the 1D N15 spectrum of uniformly C13 N15 labeled BR. These are the amide nitrogens there. That little blip blown up down here is a single nitrogen on the shift base. All right, and these are arginines and these are lysines. So you can just count these up, count the intensity of the lines, integrate the intensity of the lines like you do in an everyday organic chemistry experiment, and you'll see that the shift base should be 1. We integrate that to 1. This amide line should have 248. We integrate to 240 plus or minus 13 or so, as I've shown here. The arginine should have 21. We get 25. And the lysines, we get about, they're 6, and we get about 6. Okay? So the intensity of these nitrogen lines actually corresponds theoretically to what you should observe theoretically. And so this just shows you that, in fact, that this idea about the polarization diffusing in actually is really correct. Now, we can also incorporate this Dmp experiment into multidimensional NMR experiments. So this is a 3-dimensional nitrogen-carbon-carbon experiment. We don't have to go through all the details of this pulse sequence. Just to note that there's a nitrogen dimension here. We transfer up to carbon. We do some carbon recoupling, and there's another C13. So this is the N15 dimension. This is the first carbon dimension, and this is the second one. All right? I'm just going to show you some 2D plots of this. But what you do is you can turn on the gyrotron, and we've left this thing on for like 21 days. So you just, this is great for your graduate students. You turn the thing on, and you let the system do signal averaging for 3 weeks. All right? So even with the enhancements that we get, we need this kind of sensitivity. So this just shows you what a 2D spectrum looks like. So you start off by polarizing at nitrogen. I didn't tell you, if we go back to this pulse sequence right here, we do polarize the protons, and we transfer from protons down to nitrogen and then up to carbon. So we selectively pick out the N15 with that Gaussian pulse over there. And then you can transfer from the nitrogen to C15 to C14 right there, to C13, which is there, and C12. So this is a 2D experiment now. This is a nitrogen dimension, and this is a carbon-13 dimension. And you see you get really excellent signal noise. So these lines correspond to, because we're looking at a mixture of bacteriorhodopsin of about 1 C13 and something of the order of 85,000 molecular weight. And you can record this in a few hours of time. Probably 1 hour is optimistic, but in a few hours you can get a spectrum like this without trouble. Now, most interestingly, you actually can go around the bacteriorhodopsin photocycle right here, and you can trap photointermediates and look at their structures. And this is what we're trying to do. This is one of the nicest applications of Dmp that I think we've done so far. So what I showed you before, all right, if we go back here, you see you had 2 sets of cross peaks here, BR568 and BR555, and same thing up here. Well, that corresponds to this dark adapted state of bacteriorhodopsin, where you have a mixture present in the sample. Now we shine light on it at low temperature, and you start to drive it around the photocycle. And if we go to, I think, about 190 Kelvin or so, and we shine green light on it, we can trap this L intermediate that's shown here. So this is a J, K, and L intermediate, and these are M's, okay? Now, the reason this is interesting is because this intermediate is where this proton comes off and goes to the other side of the membrane. All right? And for the last 30 or so years, people have been studying bacteriorhodopsin, and they've imagined in the optical spectrum you only see one L intermediate. So when you do this experiment with DNP, though, now you see you get L0, L1, L2, and L3. So there are probably 4 different L states in this protein. So you have a new technique, you have new sensitivity, and you start to see a host of new phenomena that you didn't see before. All right? Now, is this an artifact, this 2D spectrum? Well, here's the 1D spectrum of BR568. That's this state right here. And you can take the 1D spectrum, well, we've irradiated at 150 Kelvin here. This is a nitrogen shift base. You see it down there in the baseline. You blow it up, and clearly you see some extra lines there. All right? So this big one corresponds to the 568 line, and these other things hanging off the low field edge here are these other experiments, all right? Other states. So this could be sequential states in the BR photocycle. We don't know that yet. So you could go from L0 to L1 to L2 to L3. They could be trapping things going down the pathway, but they all have the same nitrogen or carbon chemical shift, all right? Or it could be the protein going out in 3 or 4 different directions. Okay, we don't know that yet, and that's what we're working on right now. What we do know, though, is when you warm this guy up, what you see is that these L0, L1, L2 disappear, and what we're left with is only L3. So L3, it turns out to be the functional state. All right? And I could give you a long explanation of this, but it probably turns out that this is due to the fact that the retinal actually planarizes, whereas in these other states it actually doesn't. It doesn't actually planarize and really get ready to let go of its proton. Well, okay, so that's an application to bacteriorhodopsin. Now there are actually several other applications I could tell you about. Amyloid is one of them, but I can see I'm out of time here. So what I'm going to do is skip through all of these slides. All right? I didn't know how long this was going to take. Now let me summarize. All right. First I tried to show you how high-frequency DNP actually works. That you need these interesting new Gyrotron microwave sources together with low-temperature magic angle probes, and this is some of the instrumentation that you need. This just shows you the factor of 175. I think it's clear that in the future, as we develop new and better polarizing agents, we go to low temperatures, this number of 175 will go up to maybe 300 or 400, okay? And this is going to offer a huge number of new possibilities to study various and sundry systems with NMR. This is not only in biological systems, but there's a huge effort now in Europe studying surfaces. So zeolites and catalytic surfaces. So turns out you can polarize the surface as well as the whole molecule. All right. And finally, what I tried to show you also is that we can study membrane proteins. And what's most exciting about this is that spectra like this allow us to look at intermediates in photochemical reactions. All right. So we can trap these at low temperature into structures, and those intermediate structures will tell us, hopefully, something about mechanisms. Now, I didn't get to show you this because there's not really time, but we're also doing structures of amyloid proteins with DNP-enhanced spectra, and this is a structure of this PI3SH3 right here, and this is the sort of first calculation of the structure which matches a model that we proposed for this. So with that, I would like to thank you guys very much for your attention and for this lovely day here at the University of Richmond. And let me also again thank the people who really did this work. So.